So it's me again, Fabio Crestani, talking about distributed information retrieval. By the way, maybe should remind you that an extended version, twice as much as what I'm telling here, will be at the summer school in information retrieval, which is in Voronezh in September. I think the registration there are still open. There'll be a lot of other lectures about information retrieval. There will be other international speakers. I know for sure that there is Ricardo Baeza Yates, who is the research director of Yahoo in Barcelona and in Chile, who is going to give a talk there. Don't remember the topic, probably on web searching. And then there's Munial Almas on structured and aggregated search, and other people as well. Plus, yeah, so it's a full week event. Okay, so resuming this talk, I realize also that now is the core of what I'm supposed to talk about, and given that I have about an hour and a half of time, or less actually, I may not be able to cover in the detail as I wanted the topic. So I sometimes will skim through some of the slides which have formulas and things like that. Feel free to stop me, or probably better, you will find the references there, and you will read in much more detail the actual formula, the actual methods that I'm going to describe only superficially here. So yesterday we got the background. We got background in information retrieval. We saw what distributed information retrieval is. We also saw that we can do distributed information retrieval in different ways through different architectures. And we narrowed down on one particular architecture, which is the broker-based architecture. And so today we are going to be talking for the large part of this talk about this broker-based architecture. Quick reminder: the broker-based architecture is called like that because there is a broker. So one of these nodes in this network, which otherwise could be peer, is not a peer anymore. Is call it a super peer, called somebody who has knowledge of other nodes that are connected to it. And the knowledge that this super peer, better called broker, has is that it knows what these resources contain. Okay? It has some understanding of their content, which can be used in the way that instead of sending queries directly to these nodes are held resources, we will have to send our queries through the broker, and the broker will help us by selecting some of these nodes, some of these resources, and passing the query directly to them, and then getting the results back and fusing them, merging them, and then presenting it to us as it was a single ranking. So from the point of view of the user, submitting a query to the broker and getting the results back, the user doesn't even realize that this query was sent to potentially tens of hundreds of these resources, and their results are getting back. It's like it was sending the query to a single system. So what are the elements that are involved to get this broker so intelligent and so skillful in what it does? Okay, well, there are some processes that are involved and some phases. So the phases that are usually involved, first of all, is what is called resource discovery. So this broker need to know about the existence, about the birth of a new resource, and incorporate it into what he knows. Then there is what is called resource description. Once he knows of the existence of a new resource, he has to acquire some knowledge of that resource with respect to a number of parameters. First of all, what the resource contains. Second, what kind of queries it can accept. For example, if there is a specific query language. Third, what kind of results this resource will send back, and how then he has to use this to assemble that. Then what happens is then when it has to be able then to use this knowledge, this resource description, for other phases. First of all, a resource selection. So when a query gets issued to the broker, based on the knowledge that he has of the existence and the description of this resource, he has to decide which resource to send the query to, avoiding flooding the entire network with sending the query to each one of the nodes, but selecting only the nodes that are good or potentially good to answer that query. Then results fusion. So once the resources that have been that received the query send the results back, he has to fuse the results, merge the results, and then he has to present it to the user in such a way that is meaningful. For example, if the results are all of the same type, it just produces a ranked list. If the results of different types, like we've seen in vertical search, it has to compose these results in such a way that it shows the map, it shows, for example, the URL and the main web page, it shows some summary, for example, of some other web page, and so on. So it has to assemble the results of the data that arrive from different resources. So in the rest of this presentation, I will not talk about resource discovery and results presentations because of time limitations, and also because these, certainly resource discovery is one of the least area studied, and mostly because at the beginning of the IR we were in a scenario like a federated search, where it was actually the resource that would go to the broker, say, oh, I am a resource, please include me in your federation, and so there's no need for discovery in that case. So we'll start instead with we'll concentrate instead on resource description, selection, and results fusion. Okay, so what is resource description about? Well, resource description is concerned with getting the broker an understanding of what is the content, what is the way of handling each one of these nodes, which we say will contain a resource. What is a resource? A resource is a collection, and it's a collection. It's an index as well of that collection, and a search engine that will handle the query using that index to produce results. Okay, so each one of these resources is a full-fledged system. Okay, which if you wanted, you can go directly to, but because there are tens of hundreds of these, well, unless you really want to repeat your query 100 times, you better go through the broker. So, okay, so how does the broker acquire a description, some knowledge of these resources? Well, we need to distinguish between two environments. One environment is called cooperative environment, and this is where it's really the concept of the federation. Okay, there is a concept of a resource that says, okay, let's get together with other resources and make up a federated digital library, for example. In that case, this environment is fully cooperative. The resource can provide full access to the document, to the indexes, to the broker. Okay. Providing access to the document doesn't mean that the broker can harvest the document, but it means that he can start an indexing process, produce an index, and acquire that index without moving the documents from where they are, or taking a copy of the document. Or it may simply means that the resource will inform the broker, this is the search engine I'm using, this is the retrieval model I'm using, this is copy of the indexes. Keep it and use it for the subsequent phases that are the resource selection, the results merging. This will be the best case, and the thing is that the one that simplifies everything. Okay. On the other end, in many cases, we have what is called uncooperative environment. In this environment, a resource will enter the federation and say, okay, here I am. I will accept queries from you, but that's it. I will accept queries and give you results back, but I'm not doing anything else. I'm not giving you an index. I'm not giving you access to my documents. I just accept queries and give you answers. Okay. This is the case where each one of these resources maintain its complete independence, and the brokers establish with the knowledge of the resources or even without the knowledge of the resources. So I can establish in that case a broker even if the resources don't even know about the existence of that broker. So let's start with the easy case, okay? Resource description in cooperative environment. Well, as I said, this is very easy. The broker has access to the collection, either the collection, if it is fully cooperative, or to the indexes that are held in the collection. In that case, the broker can harvest, can crawl the collection, or can just get a copy of the indexes, and these are kept locally. So obviously, this simplifies a lot the situation, because when a query arrives, the broker can just check on each copy of the indexes that he has, which one is the collection that will likely contain documents that are relevant to that query, and just then dispatch the query in that direction. Okay? Notice that we are still not talking about, for example, a search engine that crawls everything and that carries out the search locally. Okay, the broker will use the indexes to decide which of the resources is best, and he will have full knowledge of the content of the resource, but then will pass the query to the resource that will answer the query. So the indexes are still distributed. Right. There's been several. But we are still, as I said, in a very different situation than a search engine. Why? Because each one of these resources will have its own model. Okay. So although it would be easy for the broker to decide where to send the query, each one of these resources will answer in its own way, producing a rank list which may not be comparable at all with the rank list that you get from another resource. Imagine, for example, one system use a Boolean model and therefore return a set of documents where each one of the document in the set is equally relevant, so there's no ranking. While another one use another model, I don't know, a language model, where the documents are ranked in order of relevance. Maybe another use a vector space model. Okay, it's another ranking, but you cannot compare the scores because the scores are based on totally different mathematical models. So how do you merge it? Okay, so it's still a pretty complex problem. But if you have cooperation, you can get some information. Okay, you can ask the resource, what model are you using, what is your maximum score, what is your lowest score, what is the range of the score, is that range 0 to 1, or I don't know, 1 million to minus 1 million. This is the approach that is being followed by this proposal, which is called the START, which is the Stanford Protocol proposal for Internet and retrieval search. In this case, there is really a protocol. All this information can be codified and passed between the broker and the resources. So the resource will provide content summary, so the indexes, for example, and will provide other information, other metadata about the resource. For example, what kind of query language the resource is accepting, score range, stop words, sample of results, supported fields, for example, of search, plus, as I said, content summary. So, for example, the full index. So the term frequency, the document frequency, the number of documents in the collection, and so on. Okay, this is all very valuable information that then the broker can use to modify the query, to decide where to send the query to, and so on, and then merge the results. In fact, also this proposal goes into providing a way of translating each query that the broker receives in different query languages that the different resources can have, providing filter expression, ranking expression, and so on, and also providing ways of normalizing score, or even not normalizing it, but just produce a list of where the document comes from with the source indication. Okay, so this, as I said, is very easy. I mean, you will find in the references a description of each one of the approaches that I'm presenting. The real difficult stuff comes when you have a non-cooperative environment. In this case, as I said, the resource is uncooperative, just takes query, produce result. You know nothing about it, okay? You know nothing, but you need to know something. Otherwise, how are you going to select that resource instead of another to send a query to? So the broker needs to acquire this information without the help of the resource, but still need this information. So it is important to understand that the information that will be acquired will be done without any help from the resource. So it can only be estimated. And so this estimate of the resource description that the broker will make in the techniques that I'll show you in a minute will contain errors. And the broker will need to consider the fact that there are errors there when he takes whatever decision he takes about selection or merging. So yesterday somebody, I think, already suggested some possibility, and in fact this is the one that is used, which is called query-based sampling. Okay, if the only thing you can do is submit queries to a resource, that's the only way that you can use to acquire the resource description. So, how does that work? Well, you submit some queries, some sample queries. The resource will answer you back with documents. You analyze the document and you build a description out of that. Obviously, this is simple to say. It's a lot more complex to do because first of all, you need to know what queries are you going to be sending there. Obviously, the quality of the resource description that you will make depends on the query that you're sending. What you want to do is that you want to explore the term space, the document space that resource contains in such a way that the representation that you're making is good. Also, since we are talking about sampling, when are you actually stopping this sampling? How many queries do you need to send before saying, well, I have a resource description that is good enough? These are the two things that I'll talk now, but as I said, because of all the topics that I want to cover, we'll go relatively quickly. So, first of all, how do you select the queries? Okay. As I said, the criteria that you want to follow is the queries should be as different as possible so that you explore different part of the document space, and then once you get the results back, you will, using the processes that we saw yesterday to index a document, to analyze the content of a document, extract keywords, and then build your statistics of the keywords. Assuming and hoping that the descriptions, the term that you extract there and their frequency in the documents that you're getting will be representative of the frequencies that you have in the collection. Example: if you send a query containing the word, economy, finance, Russia, okay, and you get 10 documents back. Okay, you take the 10 documents back, and you analyze in this document what is the occurrence of these words, of these three words. Then you are hoping that this will be representative of the frequency of the terms that will be in the collection. Okay, then obviously you only sampled these three words plus all the words that were contained in the document that contained these words. What you want to do is that send another query. How do you select the term for this other query? Well, you can select it from an external reference dictionary. Okay, so you have, for example, Wikipedia or whatever resource you want, or a dictionary. A thesaurus or something like this that you have external, and you pick terms randomly there and you use them to send queries. Or you can take the document that you're getting back, build your statistic, and then take some documents from that and use them to make the next query. So this is what is called the ORD and LRD techniques. And it seems that it's obviously different, the kind of thing that you're getting, okay? If you're using other resource description, this is better. You know, you're building a more representative sample because you are not picking the terms to send a new query from the query that you get back, and therefore you're not constrained on the language that the resource use. But it's obvious that if you pick terms from an external resource, then there may be terms in this external resource that are not contained in the document. In the collection. And in that case, you have a lot of what is called out-of-vocabulary terms that return no documents. Okay? This is still useful information, but you know, you're wasting a lot of time in this case because you're just sending queries that could contain no results. What is the best combination? Well, again, as in many areas of information retrieval, it's difficult to find theoretically what is the best approach to follow. Yesterday I talked about evaluation. The importance of evaluation information retrieval is that sometimes you cannot decide, you know, with pen and paper, what is the best strategy to do. You need to do some experimental analysis, some evaluation, and then find out, you know, from the result of the evaluation, which is the best strategy. For example, the best experimental strategy seems to be using what is called the average term frequency. You divide the collection term frequency, so how many times the document, how many collection contain that term, and you divide that by the document frequency, or what is the frequency of the term in the documents that you're getting back, and you build what is called the average term frequency, and so you try to pick terms random that have an average term frequency which is in the average. Okay, so terms that are kind of representative of your term space, instead of picking terms that are particularly frequent or particularly rare in that collection. This goes back to some statistical analysis of terms in information retrieval, which we have no time to cover, but there is a theory behind this on the importance of terms, which is that the terms that have an average term frequency are the best to represent the content of a document, because the very common terms are terms that usually have no really semantic meaning. If you look, for example, here, you will find that probably the most common term is, I don't know, this is very short though, but in any corpus you will find that the most common terms are they, of, and, something, words like that. Well, the very rare term, what would be the most rare term that you would find in a collection? Try to guess. A weird spelling mistake, for example. A spelling mistake that nobody do, okay, or one person did it by chance. Even a rare spelling, even a spelling mistake that is common, like, for example, I don't know, changing A and S on a keyboard because one finger is faster than the other. You know, that you will find in a corpus like the web, you will find many words with that spelling mistake, okay? But, you know, a spelling mistake that is strange and so on, that probably you will find only one single occurrence of that word, even in a corpus that have 1 million documents, okay? But it's still a spelling mistake. You don't care about that term. You know, nobody else will search with that term. So the most important terms are the ones that are in the middle. Okay, so after having sort of some time experimentally approached the issue of deciding which queries to sample, for example, here I put 2 and 10, because, for example, when you send a query, it doesn't make sense to look at a lot of documents, okay? But it doesn't make sense to look also to the first document either. The first document sometimes is not necessarily very it may be very relevant, but not necessarily representative of what the collection contains about that query. So you want to analyze the first 2 to 10 documents in the results, and then, depending on what strategy you're using, select the term from there, or use an external resource to select those terms. About the stopping criteria, as I said, another important problem is, how do we stop? How many queries do we need to send before we have a good resource description? Well, again, this is it's not a well-studied problem. There's been a lot of recently a lot of work on this, mostly from a heuristic point of view, where experimental studies suggest that after you sample about 300, 500 unique terms, then you have probably a good enough representation of your resource. But this obviously depends on the collection size. So, 300 terms on a collection that has 10,000 documents is totally different than 300 terms in a collection that has 1 million documents. Although, if you pick the term correctly, again, some statistical studies on the growth of the vocabulary on the collection size, you will see that if you take a document, okay, then you add a second document to this collection. So you have a collection that's only made with one document. You add a second document, your vocabulary will probably double or triple, okay? If you add another document, well, it's not going to go like that. So the vocabulary growth, with the growth of the collection, sort of gets a plateau. It will still increase even if you have, 10 million documents. The next document that you had will probably add some terms, but maybe it will be, very weird terms, or it will be names of person, names of location that you haven't seen before, dates. Well, although after 10 million documents, probably you've seen old dates in the history of humankind or something. But the whole spelling mistake will still be there. Okay. So stopping criteria then. Well, this has been related to work that has been done on determining the collection size. Because we need to determine the proportion of document sample in relation to the size of the collection, the proportion of the term sample in relation to the size of the term space, and also if you have dynamic collection, which is, for example, a topic of research of one of my PhD students, for example, collections that are made up of documents coming from Twitter, where you have, a huge amount of document being added every day, talking about the topic of the day, and then the day after talking about another topic, and so on. So there, the vocabulary growth is very regular, as opposed to a library where the next book that you're going to add to the library, if you were analyzing the full content of the book, will probably add not many terms to the new collection. There, the vocabulary growth is very important as well. So it depends on the kind of the collection. Without going to the details of these techniques, if the most important thing here seems to be able to estimate the size of the collection. Again, this is an important parameter that my broker need to know about when he decides where to send the query. So it's an important element of the resource description. If I receive a query and I know that I have a collection here that is very specific about the topic of the query, I don't know, Malaysian finance, okay? And I have here another collection which could be, about the whole of economy, the collection of the Wall Street Journal. Then and I know that one is 100 times bigger than the other, I may still decide I want to send the query only to this very specialized collection if the query is so specialized. So knowing the size will help me also to decide. How do we estimate the collection size? Well, there are two techniques. One is called capture-recapture, and the other is called sample and resample. Okay, and you can sort of get the gist of how this technique work. The capture-recapture technique is based on the fact that if you take X being an event that is randomly sampled document is already in the sample. Okay, so you pick a document and you look at a term and you say, oh, I already seen this term. Okay, and then Y is the number of terms that you find in N trials then you can use this basically to estimate the expectation of finding, for example, X, which is the size of your sample over the size of the collection. If you do this n time, obviously, it's n. If you assume that these terms are independent, okay, then it would be n over the size, the sample. N multiply the size of the sample over the size of the collection. Now, this is a technique that is used, in fact, also to experiment the size of to estimate the size of a population of animals. Okay, if you want to know how many elephants are left in Africa, how do you do? Okay, you go, you're going to gather all of them and then count them. It's going to be difficult. Okay, you can maybe take one. And I don't know, stamp it, put it something on here or something, and then let it go. Then you try another day and see if you get I got the one that's already been stamped. Okay, so basically, if you take two samples and you look at the interception, the number of elephant that you got yesterday, the number of elephant you got today, and how many of the elephant that you got yesterday you got also today, you can use this to estimate the size of the collection if you do this several times. Okay, the product of these two, the size of these two samples divided by the intersection, based on the fact that obviously the intersection is the product divided by the size of the collection. Okay. So this is what is called capture and recapture. The analogy with capturing people, capturing animals, is there. And then there's what is called sample resample. This is similar in a way. You randomly pick a term from a sample, and then so you have the event A, that is the event that some sample document contains the term T. So the probability of getting this event is the document frequency of the term in the sample divided by the size of the sample. So how many documents contain that term over the size of the sample that you just made. And PB instead is the probability of B is the probability in an event of, that some document in the resource contain the term T. So here is basically the same statistic calculated on the collection. So the number of documents that contain the term T in the collection divided by the size of the collection. Well, if you assume, and the way to have this assumption holding is that to do a lot of these samples, okay, that the probability of getting a term in your sample is the same of the probability of getting it from the collection, then you can estimate the size of the collection by multiplying it, basically your term frequency in the collection of the term T, multiplying that by the size of the sample divided by the frequency of that term in the sample. Okay. How do you get these two values? Well, you get these two values because, you get this value because it's from your sample, so you can do it. You get this value, that how many times that particular term occur in your collection, your source, because one of the things that even non-cooperative systems do, like Google, for example, is that they will, if you put a query with a term, it will tell you how many times that terms occur on the web, on the collection, basically. Okay, so it relies on the resource giving you the correct number, the correct document frequency of the query term. Okay. So basically, you send the query term T to the resource to estimate, to get from the resource how many times that terms occur in the collection. You repeat this several times with the several terms, and then each one, every time obtaining an estimate. And then what will happen is that if you do this a lot of times, you will see that you also have you can take the average basically, and you will see that this is a good estimate of the collection. This technique is being used, for example, to estimate the size of the web. Okay, and you can use it at any point. Obviously, relying on the fact that the resource will give you the correct document frequency. which, as a matter of fact, for the web, it's a problem as well, because if you send the same term to Google and to Yahoo, you get different term frequencies. Okay? Why is that? Well, because because each one of them sees a different size, a different portion of the web. None of them sees the full web. Okay? So you can estimate the size of the web according to Google and the size of the web according to Yahoo, and hope that, well, it's not in the middle. It's probably more than each one of them. Okay, so again, this was a quick summary of what resource description is about. Here's some essential references on this. Right, okay, so any questions about this? Feel free to, as I said, to interrupt me anytime. Right, okay, once I have obtained my resource description, then this resource description is held at the broker. Okay, obviously the other related issues to resource description is, when do I know when my resource description become obsolete? Okay, obviously with a very dynamic collection, this can happen very quickly. Okay, if my collection gets 10,000 documents added per day, and it's a collection like, I don't know, Twitter or a Newswires or something like this, where it reports events happening on the day, and where these events can talk about new places, new people, new companies, and things like this, then my resource description becomes obsolete pretty quickly. If instead we are talking about a library or I don't know, patent searching or something like this, then, you know, my resource description will last a little bit longer. Anyway, I have this resource description. Comes a query, my broker has to use this resource description to decide which resource should the query go to. This is called resource selection. So, what kind of techniques do we have for resource selections? Well, there are three kind of techniques. Okay, the one being the one that are most studied, and the first one is called lexicon based. Okay, so the lexicon based techniques, it's used roughly in this way. Then obviously there are many different approaches that are slightly different one to another. But what it does is that the query arrives. We have the resource description. We assume that the resource description is a good sample of what is contained in the resource. So the first thing that I can do is that I use each one of these resource description like it was a document. Okay, as a matter of fact, it's a set of terms, so it could be a document. Okay, it's just a super document that represent all the generic term distributions of the term in that resource, and I run my query against this description. The description that is ranked the highest, according to whatever model I have, language model or vector space or whatever, if that resource matches better, if the resource description matches better my query, then I assume that the resource will be the best place to send my query to. Okay? So this is what is called lexicon based. Okay? The broker calculates the similarity of the query with the resource description using the statistics of the terms that we have built using the query-based sampling technique that we've seen before. Right. Obviously, this depends very much on the quality of my resource description and the fact that I'm assuming that my resource description will contain a good representative sample of what the resource contains. The document surrogate based approach instead, well, this is obviously the lexicon based works, as I said, it depends on the quality of my description. So if I have a fully cooperative environment, the quality of my description is perfect. It was given to me by the resource, so it will work perfectly. If I'm using query-based sampling, well, it depends how good is my sampling. The document surrogate based approach instead doesn't rely on any cooperation with the resource. In addition to using the resource description, it would also use some sample document from each resource. Okay, so it will take this query, send the query, or look for similar query that in the past were submitted, and compare this query with past query that were submitted. Or it will take this query and sort of having in the resource description some sample documents of the resource, it will compare this query with the sample documents, combine the results of the sample document with the results of the matching with the resource description, and make a selection like that. So it will use additional information than the lexicon. It uses also a sample document from each resource that it contains in some part of the resource description. The third approach, which is called the classification base, instead is less used because what it basically requires is that you create a classification, often hierarchical classification, of the resources that you have. In such a way that each one of these resources gets sort of classified in this classification, and therefore when the query comes in, you assume that the query is like a document that you need to classify in this classification, and you just pick the resource where, if you were to put that document in one collection, you would put it to. So if that document, if that query, which is representative of a document, should go in that resource, then probably that resource is the best to answer my query as well. And you can have a ranking, obviously, the best, the second best, third best, and so on. So the broker basically classifies resources into a topic hierarchy based on the query-based sampling technique, and makes selection decision based on the matching between the queries, the query that he receives, and the categories of the hierarchy. Right. Okay. So I'll skip many of this detail of these techniques. So as I said, the lexicon base, assume that there is a sort of super document. Okay, the sample that we are making, we send the queries, we get some document back, we analyze the terms, we put it in the description. We send some other queries, analyze the term, put in the description. Once we have the description will be a set of terms with their weight. If you look at it, this is exactly the same representation that every single document will have. Well, let's assume that this representation, instead of being a collection of documents, is a super document, a big document that is the concatenation of all the documents that we got when we were sampling. Well, fine. Then I compare my query with this super document, and the super document that answers best my query determines the collection, the resource where I will send my query to. The two techniques the two best known methods following this approach are Cori and Gloss, which I think I better skip. Okay. The Cori, well, they both use this super document approach. Cori basically use a probabilistic model to estimate the probability of a term given a collection using what is called the Okapi formula, and then given that the query is a collection of terms, it will estimate the probability of a query given the particular collection that you're doing. This can also have a generative probability interpretation, which is what is the probability that that query could be generated from that collection. Okay, so once you have that, then you can just say, okay, if this query has the higher, if this resource give me the highest probability of generating, sampling, those collection of terms that are the query, that's where I should send my query to. Okay, so you basically have a goodness, related to that. Sorry, this was Cori. Gloss, we assume total cooperation. So we can just, again, evaluate the similarity, and then I just pick the collection that has the best match with my query, and again, because we assume cooperation, this is relatively easy to do and also reliable. The document surrogate approach assumes instead that for each one of these resources, not only I have the term frequency, and therefore I have the super document, but instead of keeping having the super document, I'm also keeping sample of the document that I go back. So I don't destroy the documents when they come back from my resource. I analyze them to get the term frequencies, but I also keep them. Okay? So for each one of the resources, I have my resource description and a little pool of documents that came from there. This pool can be augmented, every time a query gets submitted to the broker. Okay? A new query comes, my broker sends it to you and gets the document back, and then pass it to the user, but keep them as well. Okay? So this pool increases the more we use the broker. Well, then the document surrogate approach says take your query, compare it, and obtain a score for each resource of the goodness of the resource. That is a combination of the super document approach and of how many good documents you find in the sample that you get for each one of these collections, of this pool that you have. And the slightly different models depending if you use the REDE or CRCS approach. Again, which I skip for time reason. Okay. Now, there's many other techniques. These are anyway the most used one. One relatively funny thing is that one could say, well, being this information retrieval with a lot of evaluation, it should be easy to calculate which one is best. Well, yes and no. Now, I'm showing you this as an example, of, again, what is the problem with information retrieval, which is there's no technique that is good for every case. So this one, for example, we are using a collection which is called the Trake-4 K-means. Basically, you take basically it's a collection of collections. Okay, I'll talk about that later. We are taking long queries, and this is what is called precision after 5 document, precision at 5, precision at 10. Yesterday we talked about precision and recall. Okay, so precision at 5 is that after you've seen 5 documents, how many are good? Okay, after you've seen 10 documents, how many are good? Okay, and so on. Precision at 10 and so on. Forget about the cutoff years. Is how many collections you're actually looking at. So if you're selecting the best collection or the best 5. So as you can see here, according to with long queries, with cutoff of 1, the technique that seems to work the best is Cori. Good. Cori works. Well, you're using slightly different collection. You're using short queries. Well, what is the technique that works the best? CRCS. Okay. You are using these techniques are all called track. Okay, these means that they are very similar. Okay, they are all coming from the track test bed, which is a collection of news mostly. There's 100 collections. This is I think slightly less. This is 60 collection. This is 100 collection. Okay, so this collection here with short query, but is a slightly different collection. Cori is the worst now. Okay, and CRCS is again, actually in REDE is the best. Okay, this is with same query, but slightly different collection. Okay, and again, if we take, for example, a collection like the .gov, which is a more web representative collection rather than news, short queries, as short as that, again, what we have, the best is Cori. Okay, so there's no way, basically, unless you do some experimentation, to know which one is best. Okay, because there are so many parameters involved. The size of the collection, how many sub-collections, what kind of measure you're using, what length is the query, and so on, that each one will determine different performances at the end. Okay, and here is some references about resource selection. Feel free to ask questions. Okay, so last of the 3 phases that we are looking at is the results merging. Okay, not to be confused with data fusion, which I'll explain in a minute. So results merging, well, using the resource description, we selected which collections we are sending the query to. We are now getting the results back from each one of them. One sends me 10 results, the other sends me 100. One sends me 10 results with score that goes from 0 to 1. One sends me 100 results with no scores. Okay, just a ranking. Okay, how do I merge them? Okay. Also, what if I find duplicates? Okay, should I remove them? Should I keep them? Should I make use of them? Okay. In fact, this is also another problem that we haven't touched. But if I find that two resources here have a lot of document in common by my query description, should I send the same query to both, or should I just select one? Okay. If I send, there's advantage. If I send it to only one, well, I'm saving bandwidth. I'm saving that you have to remove many of the overlapping results. But if I send it to both, I can get two ranked lists where I have some reference point that I can use to then normalize the score. Okay? If I find that one document in this collection is number 3 and has score 0.5, and here in this results list it comes at position 10, he has score 1033. Okay? I can say, well, 0.5 here is equal to 1033 here. Okay? And then I can use it to normalize the score in which one, and in each of the two ranked lists, and merge them. Okay. This also brings me to the difference between results merging, which is complex because of this normalization, with data fusion. Data fusion is done when you know for sure that each one of these resources have exactly the same engine, exactly the same model. In that case, the only thing no, sorry. It's when I. Well, I'll explain you later because there's a feature as well that explains it. Okay. So data fusion is different. Okay, because we have a single resource but multiple retrieval models. If instead I have the meta search case, this is like the meta search case. Okay. If I have instead the classic, let's say, case of distributed IR, where I may have the same, I may have totally different collection, but the same retrieval model. That's not a problem, okay? Because the score that are coming can be matched to one to another. Okay, so the two issues in results merging is duplicate detection and removal. This is not easy because, for example, in web search, this is a big problem because about 1/3 of the content of all the web is a near duplicate of something else. Okay, meaning that it's not exact mirror of that page, but it contains exactly the same content reshaped. Okay, so should I show you, the same news, for example, being reported by all the different newspapers that talk about it, maybe all originating from the same newswire, or should I not? This is an issue for search engine. Here, similarly, we have to detect, duplicate, and then remove them. But the most important thing is that we have normalized and merged the scores. Again, difference between cooperative environment and uncooperative. In cooperative environment, well, if it is really fully cooperative, we can impose to each one of these resources to use the same model. In that case, the merging will be very easy. It's just a merging of documents coming with the same scores, with the same scores model, and therefore I can just, put them in the ranking, the position where they should go. If there is cooperation, but each one is using a different model, but I know what model they're using and the parameters of this model, I can, when the documents come, use this information to produce a good merging. Or again, if there is full cooperation, I could say, all right, instead of giving me just a pointer to the results, send me the full text of the document. So I take the query, send it to the resources. The resources send me back the documents. I take the document, run a quick indexing of the pool of documents, and then produce my own ranking. Okay? And this will be perfect because it's all made. Okay? And I don't need to rely on the scores that I'm getting from the resources. Right. So instead, the problem, and so this is easily done, for example, with when we have cooperation and we know about the scores that each database give us. We can normalize it easy. In that case, in the approach proposed called by Corey, we can calculate the score of each document to put in the ranking as a combination of the scores of the documents that the document received from their resource and the score that are given to their resource. Okay? So basically a way to say that the first document from the best collection is probably better than the second document from the second worst collection, the second best collection. Okay? So I have a linear combination of the score of the document, normalized obviously, and the score of the collection, normalized. In non-cooperative environment, it's a lot more complex, and I need to use my resource description. Again, there's different models being proposed. These models, these two models, which I again skip the detail, relies on the fact that you have this collection selection index, this representation that you build of the resource, and also you have some sample documents. Okay? If you have some sample documents, then you can compare the score that you give yourself to a collection, to a document coming from the collection, and the score that that collection give it. Okay? And use some linear regression model to say, okay, if these documents get this score from me, but get this score from this collection, these other documents get this score from me and this score from the collection, you can basically use this relatively, painlessly, to calculate, or you should normalize the score that is coming from the collection to be a sort of, to match it to your score. And once you've done that for different collections, for example, if all the resources use a retrieval model, you need to do this only once. Okay? Once you have normalized the score, then fine, you do the merging. If each one of them use a different model, then you have to do it for each one of the resources. Get a mapping between the score that they have to your score. And then, once you've done this mapping from that score to your score, then you can translate everything into your score and do the merging. Okay? So this is called SSL model. Okay? I'll skip this for now. Okay? There's other approaches. One is called SAFE, and then the START, CVV, and so on. As I said, this is different from data fusion. Why? Data fusion, for example, the example is the meta search that we talked yesterday, where you have a search engine that cannot be bothered to build its own index, takes your query, send it to Google, Bing, Yahoo, gets the results back and present it to you. Okay? There, the difference with distributed information is that the collection is the same. We'll assume it is the same. So Google, Yahoo, and Bing are indexing the same thing, but with different models. So this is called data fusion, and again, this has been studied quite a lot. The easy technique that for simplicity, many search engine meta search engine uses what is called the voting principle. If a document gets scored the highest by 2 out of 3 of the search engine, well, it's good. Okay, better than the one that gets scored the highest by only 1. Okay, because one receives 2 votes, the other receives 1. Okay, this is very easy. More complex techniques especially when you get very different ranking coming from the different search engine, are, for example, round robin. Round robin says, I'll pick the best from Google, followed by the best from Yahoo, followed by the best from Bing. Then I take the second best from Google, second best from this, and second best from that, based on which one I trust more of this search engine. Other techniques, COMMZ, COMSUM, COMMAX, and so on, are if I take the combination of the basically the average position that they get. So, for example, one gets position 1, 1, and 7. Well, 1 plus 1 plus 7 divided by 3 is the position that it would get. Okay, and if I have some preference that I can give to each one of these search engine, I would multiply each score by the preference that it gets. Okay, COMSUM, it's simply my ranking list will be, I will give at each document the maximum that it gets from each one of the search engine that it gets back. That's a COMMAX. COMSUM is simply the sum, as I said. It could be 1, 1, and 7. Well, this document gets 9. Okay, the document that gets 1, 1, 2, and 3 will get 6. So we got it on top of the one that gets the other. Okay, and then the minimum is the other way around. You give it the minimum score that each search engine gives. Or you can have logistic regression, which converts ranks to estimate probability of relevance. It's a more complex document that I believe no current meta search engine uses. Okay. Okay, let's skip the overlapping case. Okay, and this is some results of the some references for results merging. Okay. So, by the way, you should get. I sent to Alexander, copy of the slides, and I said he will put it on the website. So, this was a quick, painful, I suppose, overview of the broker-based distributed information retrieval architecture and components. I want to finish here relatively quickly to give Mark his time talking about quickly about evaluation, how DIR evaluation is different from IR evaluation, and what is instead the same, and a couple of slides, about application of DIR, because we already talked about that when we talk about the motivations. So DIR evaluation. Objective, test collection, and evaluation metrics. Easy, because DIR is a subpart of IR. Okay, so and IR has been evaluating techniques and so on for over 50 years. So a lot of the things can be reused, can be imported into evaluating DIR. There are some differences, though. One main difference is that here we have different resources. So the test bed, the evaluation framework that we want to build, which again, I remind you, they are called test collections, and a test collection is made of a corpora, a collection of documents, some queries, and some what is called relevant assessment. So known documents that are relevant to that query, which your search system should be able to find and rank in the highest position as possible. And these have been manually checked to be relevant to the query. In some case, well, there's many techniques of doing this manually checking, always pretty complex and painful to do, because imagine if you have a collection of 10 million documents, how do you know that given a query there's only 10 relevant documents in the collection? The only way of really knowing it for sure is if you go through all these 10 million documents one by one and check if it's relevant to the collection. Not possible, so there need to be, again, some sampling techniques and so on, and some people with little to do than just having to read all of these documents or a sample of these documents to find if they are relevant or not. So As I said, the main difference is between this text collection and the standard text collection in information retrieval is that these can be disjoint collections. So each one of the resources may have no document in common, or they can be overlapping, and overlapping to whatever degree. So how do we build this collection? Well, we have a lot of collection that we develop in information retrieval, big and small, with lots of queries and so on. One easy technique of building evaluation collection for distributed information retrieval is to take these big collections and break it up. We can break it up by source, for example. So, for example, the track 1, 2, 3 collection have documents from Wall Street Journal, Financial Times, San Jose Mercury, Associated Press, and so on. Well, we just take each one of these resources. There's about 100 of these resources. We can even break up resources saying this is Wall Street Journal, year 2000 to 2005. This is Wall Street Journal, 1990 to 99. Okay. We assume that there are 2 collections, okay? So this is one way of doing it. This is the size of this collection. Or we can take a collection, say a huge collection, and say, well, instead of dividing it by source, let's divide it by topic, okay? So we take all this huge collection from different sources and say, here we put all the documents that are about economics, here all the documents about sport, politics, health, I don't know, Italy, and something like this. And this is the way of doing this is by clustering the documents, using, for example, k-means. Okay, and so you have a lot of different collection, roughly, about different topics. Or, for example, in the case of a web collection, that's easy. For example, this is the .gov collection. You take all the subdomains, or as many subdomains as you can. In this case, is 100. You have, for example, NASA, was that the propulsion laboratory or something like that, and then the court cases, and so on. Okay, and you divide it like that, and you assume that each one is a server and a resource that is independent, and so on. You can see also in this case they vary quite a lot of documents, and you can have, in this case, many duplication because, for example, you can see there's many with NASA. There's NASA here, there's NASA there, and so on. So the same document may appear in different places. And you have collection, almost 1 million documents to very small. Okay, what about the metrics? The metrics, well, there's no point inventing new metrics. I mean, IR has developed a lot of those metrics. We've seen the 2 major ones, precision and recall, yesterday. Average precision, and so on. And we use all the same. The important thing is that what is the benchmark? What is the thing that we want to be as close as possible? Okay. So if I build my DIR system, what is the best performance that I could have? Well, some people say the best performance that you could have is that if instead of being having to go through the resource description, the resource selection, and so on, you take all these collection, you put them into one, and you search that one. You index that one, you have complete knowledge, so it's like fully cooperative, and you don't even have to do any resource selection, because it's one single collection. Okay? So, in theory, the best performance that you can get from a distributed information retrieval system are the performance that you will get by taking all the collections that are in the distributed environment, put them all together, and index it with one single search engine, one single model. Well, as a matter of fact, DIR is better than that. Okay? Why do you think it could be better than that? Well, because of the fact that this aggregation, which is what a search engine doing, it uses this model, one model fits all approach. So, here, for example, I may have, Michigan.gov. These are probably documents that the Michigan government is producing. They may be totally different in style, in length, in content than the document produced by NASA, for example, or the contracts directory of the government, okay, which contains only contracts than the government does with whatever body. Okay, the language is different, the length is different, the terms that are being used are different. So the same model that will work, the same model cannot work the same way for this contract and the Michigan. So a distributed information material will work better if it says this query regards contracts. Then I pass it to this resource that contains the contracts, which has a search engine specifically tuned, a retrieval model specifically tuned to answer queries that are related to government. So it turns out that DIR performs, some DIR techniques perform almost as well as IR, but in some cases even better, much better. So that is one of the motivations why, for example, some references of some of the application of DIR. And in particular, we saw yesterday the vertical search. The fact that now many search engines, because they get a 3-word query, they don't know what you mean for that. What is the best thing to do? Well, the best thing to do, instead of giving you a ranking that contains, merged together all the things that you could possibly want from this 3-word query, they aggregate one single result which contains all the information about the best results that you will get with different interpretation of that query. And then, hopefully, that's the good thing. So, application, we've seen already vertical search. I won't talk about that anymore. But other applications that we have is blog distillation, expert search, and desktop search. Vertical we saw, blog distillation. Okay, so this is another area of research that is pretty current. For blog you have to subscribe. Okay, you want to subscribe one blog that talks about something that you're interested. Now, how do you know that blog talks about some topic that is of your interest? A blog is made of posts. Okay, so probably if you do this manually, you look at many of the posts in that blog, and you will find that with many of them, will give you information that you like, opinion that you agree with, and so on. So the relevance of a blog feed is given by the relevance, or the aggregated relevance of the posts that appear in there. Okay, so how do you select what blog to subscribe, what blog feed to subscribe? Well, this is a typical distributed information retrieval problem. You have a blog feed which is made by many posts. You have to find out which one aggregation of this post is best for you. And obviously you can start from DIR, but then you can improve this model by using, for example, the temporal dimension. You probably want the blog that talk about the thing you're interested recently, as opposed it talk about it last year and now it doesn't talk it anymore. Okay, so that's one application. Expert search. What is the expert search? It's the task of identifying an expert with a given expertise. This is very common for intranet. It's very common in enterprise search and something like that, where IBM has a problem, want to find out among his 20,000 employees which is the expert on this. Well, how do you know which one is the expert? Well, you can, for example, how do you know what I'm an expert of? Well, the best thing to do is to look at my web page, or my publications, maybe my CV if you have it, maybe my post in blogs, and so on. This, if you take all of these and aggregate it, that collection that represent my output will contain what I'm expert. Well, then what do you do? If I have this for each one of you, and I want to select who is the expert here on food in St. Petersburg, okay, I just do a resource selection, basically. I need to look at each one of your collection of things that you wrote, that you know, and something, and select the best one, given the query, which is food in St. Petersburg. And finally, desktop search. Again, similar problem. What the problem here is made more complex by the fact, desktop search is basically, I'm going to search my disk in my machine, okay? Laptop or desktop, and now it's the same, okay? So in this case, I want to identify which file contain information that I'm searching of. Well, what do I have to select? First of all, I have to select the type. Is this query that I'm sending, requesting something like a picture? Is it requesting something like a piece of text that can be contained in a Word document or something like that? Well, I have to make a resource selection on the type, and then select each one of the document, then fuse the results. Okay, many desktop search systems that are built into a desktop are not very sophisticated, but if you're doing this on a server, where you have a lot of users, where you have a lot of documents, you need to use more complex techniques. Okay, and that actually concludes my talk. Any questions about these topics that were covered today? I had to go pretty quickly on that, but I hope I gave you a flavor of what distributed information retrieval is, the problems that are there, an understanding of the classification on the areas, let's say, that are important in distributed information retrieval, and then you have the references there to get deeper if you like. Okay? No question? Well, thank you.